So, today we will be talking about friction. You all know if two surfaces are in contact with each other, they can exert frictional forces. For example, if my hand is on this table and I am taking my hand in the forward direction, so it is slipping on the surface. So, the two surfaces are in contact, this surface here and this surface here, and as I move, the the surface of table exerts a force on my hand in the backward direction and hand exerts force on the table in the forward direction. So, this is the frictional force which opposes relative slipping. Any two things, when they are in contact, they can exert this kind of friction. This is a glass tumbler here and this table surface is here, and if I try to push this glass tumbler very slowly, I exert a small force on this. I exert a small force on this. I am exerting a force and it is not slipping. Then also this table surface is exerting a force on this surface in contact in the backward direction, and that is why I am pushing it towards left, but still it is not going because table is exerting a frictional force in the opposite direction. That is known as static force. There are certain rules. The magnitude of this force depends on the surface roughness, the material of the surface, and so on, and also how much is the normal contact force, proportional to that. If it is slipping, it is just multiplication of this frictional coefficient and this normal force. If it is not slipping and it is static friction, then the force will be less than or equal to this frictional coefficient mu times the normal force n. So, these are rules. Liquids and fluids, they also exert some kind of a frictional force. That property is known as viscosity, but essentially the same thing. The force is opposite to the direction of slipping. So, if some ball or something is going in water, water exerts a viscous force which will be opposite to the direction of motion of this ball with respect to water. Similarly, for air and gases and so on. So, I will start my discussion with a very famous old experiment known as card coin experiment, and you know what it is. You have a glass tumbler and you have some kind of card, and then you have a coin, card, coin. So, you place it here and then place this coin here and flick this card, and then this coin gets into the tumbler. So, let us do the experiment and see. So, yes, what is the popular explanation of this experiment? The popular explanation is, it is presented as an evidence of Newton's first law or so called law of inertia. The coin is at rest on the card and the card is flicked. So, they say that the card moves, but because of this inertia the coin remains at its own position. So, coin remains here, card goes away, and therefore, it gets into this tumbler. So, let us see if I do this again. Here is the card, here is the coin, and let us do it again and see what happens. Yes, it does go. Okay. So, one more time. So, let us take this card here and let us put it here, the coin, and then flick. this time the coin did not get into the tumbler. If I do it again, it does not. So, sometimes it goes and sometimes it does not. So, the explanation that because of inertia, because of Newton's first law, the coin remains at its own place, and since we are only flicking the card goes away, and therefore, the coin remains at its own place, and once card is not there, it falls. That explanation had some difficulties. So, sometimes it goes, sometimes it does not. So, let us understand it with the help of this friction that we have discussed. The qualitative part is that once this card start moving in the forward direction because of the flick, the coin and the card, there is a relative slipping between these two. Once the card moves in forward direction, then the coin slips on it in the backward direction, and so the card exerts a force on the coin, frictional force in forward direction to oppose the slipping. So, it is not a case of Newton's first law, it is not that the total resultant force is 0. Because of this friction, there is a resultant force in forward direction that takes this coin in the forward direction. How much before this whole card goes away, how much it has gone, that will decide whether it will fall inside this or outside that. So, let us do some equations and equations of motion. Let us write equations of motion and understand when this coin will get into the tumbler and when it will go out of the tumbler. We will have to do some modeling for this. So, our first assumption will be that the friction between this glass and this card surface, that is very small. So, we will neglect that, and friction between the card and the coin, that we will take into account. So, that is our assumption. Under that assumption we will be working, and the radius of this is important, length of this card is important, length of this card behind this coin, this is important, because that will decide when it goes away. So, how much distance it has covered. So, this is the distance that it has to cover when it goes away. So, all these things we will assume. So, let us say that our card has length L. Essentially, this is not the full length of the card, it is the length behind this coin. When the coin finds that the card is gone away, that length is L. You take mass of the card to be, say, m, and then you may need mass of the coin, let us call it small m, then the friction coefficient between card and coin, let us call it mu. Then I am flicking. What is flicking? Flicking means I exert a force, horizontal force on the card. So, that force is applied for a very short time, delta t. So, some force capital F is applied for some short time, delta t. So, that is the flicking. So, force during flicking that is F, and the duration of flicking that is some delta t, and we will assume that in this duration this F is fixed, is constant. During this flicking, whatever time it takes, during that time a large force F is acted, and that force remains constant during this short time interval delta t. So, these are the things. So, what will be the equation for first, let us say, coin? So, what is happening? You have card, you have coin, and because of this the card is moving this way. So, the coin, it's slipping on the card in the backward direction. So, there will be some frictional force here. Okay. And if you look at the card, there is a frictional force on the card also, and that is in the backward direction. So, we have to work for coin and also we have to work for card. So, for card, if you see the first during the flicking, let us say during the flicking, the time interval is very small, remember. During the flicking. So, what are the forces on the card in horizontal direction? First is this force F, which is in the forward direction, and then this frictional F. This is the force. This much force is applied on the card. This is the force with which I am flicking, and this is the frictional force because of this coin, because as it moves it slips, and therefore on the coin the force is forward, on the card the force is backward, and therefore this is. And if you multiply this by delta t, you know, this is impulse, this is the change in the momentum. So, it will gain a velocity v. Originally it was rest. In this time delta t, it gains some velocity v, and this force times this time interval, that should be the change in momentum, which should be m into v. And since this f is supposed to be large, this delta t is small, but this f is large, and hence you can neglect this friction here in presence of this f, and then you have v equal to velocity equal to f minus f divided by f delta t divided by m. So, that is the velocity gained by the card just after the flicking, and this delta t is very, very small. So, you can think that the card has started moving with velocity v, and in that time, that small time delta t, the coin will not gain much of the velocity, but after that this friction will be effective. So, how much time does it take for the card to pass this coin? So, if the length is L and this card is moving with some velocity v, and then the time will be L divided by v approximately, not exactly, approximately, because the coin is also moving. So, that mathematics you will be doing. So, I will assume that the movement of this coin is small, and so L is the length which is moved by the card before this coin finds no card beneath. So, that time t is L divided by v, and that is L divided by f here, delta t here, and m here. Now, look at the coin. This delta t time is small, so we can neglect that, and then after that you have the force is only friction. So, F is equal to mu times n, which is mu times m into g. There is a frictional force, and hence there is an acceleration, and that acceleration is F divided by m, and that is mu times g in the forward direction. So, the distance travelled by the coin delta x distance traveled by coin in this time interval, when it finds no card below it. So, that will be half into A into t square, and that will be half into mu into g, and t square means L square here, m square here, and divided by this f square here and delta t square here. This coin has to move this much distance in the forward direction. So, the coin cannot remain at rest at its own position because of this friction present. It has to move in the forward direction. But then if this delta x is smaller than the radius of this tumbler, if I assume that the coin was right at the center and then it is moving forward. So, the distance moved, if it is smaller than the radius of this tumbler, then the coil will ultimately fall in this. So, for coin to fall in the tumbler, this delta x, for coin to fall in the tumbler, this delta x should be smaller than r. This should be smaller than r. So, coin falls in the tumbler does not mean that because of inertia, because of Newton's first law, the coin remains at rest and the card moves. Coin also moves, but the total distance moved by the coin before this card goes away is this much, and if that happens to be smaller than the radius, then it falls in the coin. So, for a successful demonstration, so that the coin does fall in the tumbler, what you should have? You should have a smaller frictional coefficient. So, the card should have a smoother surface. Smoother the surface, more likely the coin to go into the tumbler. Similarly, length, this length should be small. You should not take a long card. If you take a long card, then the chances are the coin will fall outside the tumbler. Then mass, this is the mass of the card. So, that also is important, should be light. If this mass is larger, if your card is heavy, if this mass is larger, then this quantity will become larger and it may be more than radius. And of course, this flick, this force flick, it should be large. If you want this to be smaller than r, the chances should be bright that the coin goes into the tumbler, this should be large. So, you have to flick very hard. If you flick with a much smaller force, perhaps the coil will go outside the glass. So, that is how the things work, and that is why you saw in some of the cases the coin fell outside the tumbler, and in some of the cases it went inside the tumbler. Now, a similar experiment you can do with this matchbox and a coin. I will show you the experiment and you will do the explanation part. So, in this matchbox we have this drawer in which all these sticks are there and this cover. Between this drawer and this cover we can put this coin. So, now the coin is between this cover and the drawer, and I can push this coin so that it is at this level. Then I hold it from here and hit this other part of this matchbox with the fingers. So, let us see, and you see what happens to the coin. So, the coin comes out of the matchbox. So, what you have to explain? You have to explain why this coin is coming out of this matchbox.